The course had 3 parts. I remind you, the laws, then the relations between properties were also known as analytical thermodynamics. And the third part was about power and refrigeration, or applications, or the source of this discipline. So power, which includes refrigeration, because without power there is no refrigeration. Power is a challenge, is everywhere, not only in the traditional areas called, mechanical power to electricity and so on, and also refrigeration to air conditioning and on and on. A lot of this, let's say, growth of this particular domain has to do with what you read in the news about, saving the earth and on and on and on. And so today's topic is about, what about that, What about providing power in the so-called renewable sense? How about solar power? How to capture it intelligently, and what lessons do we learn from this particular exercise? But here I'm talking about solar collectors, or the capture of solar power for the purpose of producing the old acquaintance, which is mechanical and then electrical power that moves things. So the idea is about power regardless of scale. It could be for a big application or for a tiny application. So this sort of attitude of asking questions that lead to answers with general applicability is called paying respect to the fundamentals. In other words, truths that reside at bottom. I told you more than once, I think, fundamental is not about the infinitesimal, sub particle. Fundamental is about an object or a configuration that is in the foundation. Another use of the word fundus in Latin means bottom. In the foundation of every pedestal, of every statue. The 2 examples, because the way I teach is with examples, not with general formulas, are about solar power, this very useful juice, in 2 settings. One is the terrestrial setting, meaning around us here on Earth, and the other one is in space, meaning extraterrestrial. On Earth, there are many phenomena that conspire against you, the thinker who wants to draw power from the sun. And one of them is that these things that get hot on the ground, such as solar collectors, have the natural tendency of cooling off because the ambient is cold. All right? And from this first aha comes the simplest model, meaning a drawing that's a very, very cheap facsimile of an actual object called solar collector and then solar power plant, which is this one. A one-dimensional drawing, meaning from cold to hot. Up here is the temperature of the sun as a source of a stream of heating called Q dot S. S means sun. And then here's the collector, which is a surface that intercepts the heat current from the sun. This surface has a size. By now you know that size is kind of synonymous with cost or an item of great concern for your well-being. The collector has a temperature that will be very soon the lone degree of freedom in the, let's call it morphing of this particular drawing. The collector could be kind of warm or maybe not so warm, depending on what we do to it. And at the bottom, we have the ambient temperature. One thing happens by itself is the heat leak from the collector to the air that bathes it. So that's called the Q dot 0. Another thing that happens to the collector is the maker of the collector, who draws a heat current, just call it Q dot, for the purpose of driving an engine that produces power. I will draw this engine not only crudely, but I will assume that the engine operates reversibly, because this allows me to capture the physics of it in the simplest analytical form. So the engine produces a power output, W dot, while rejecting necessarily the difference between this Q dot and this W dot. And the object of the game, in other words, the promise that I make to myself, is to figure out how much W comes from this particular expensive item called capital A. I cannot do much about the sun because that is the oldest book was written about it. I have no input in that part of the story. I help myself by assuming that the engine is operating reversibly. That means that the answer to my question would be this Q dot and then the Carnot efficiency T0 over T. I confessed already that this T is something I don't know. This is the degree of freedom. The temperature of the collector is valuable if we get to know it. And next, in other words, I'm constructing, the model is a simple drawing. The mathematics representation of the model is also simple. And I'm putting on the blackboard those simple statements. One is already here. The other one is that the heat leak called Q dot 0 refers to convection. This heat transfer rate is proportional to the size of the object called capital A. U is a heat transfer coefficient. And the temperature difference T minus T0 is the key factor, the one that is proportional with the heat leak. For quite a long time in this domain of solar power engineering, researchers were concerned with a figure of merit called solar collector efficiency. I tell you about this efficiency for historical reasons, because it is not, from my point of view, is not the way to go about the thermodynamics of solar collector power plants on the surface of the Earth. But the so-called collector efficiency is defined as the ratio of the actual heat current delivered by the collector divided by the heat current intercepted from the sun. And as you can see here, this Q dot is the difference between Q dot S and Q dot 0. The efficiency depends on all these things, including the temperature of the collector. I told you the proper word for so-called efficiency is yield, or return to the user, in this case, you. Except that in this particular formula, the thinker is positioned over here and is asking questions about the heat delivered by the collector. The efficiency depends on T. The efficiency could be high, it could be low, and it could also be zero. Think of it this way. As the temperature of the collector goes up, so does the heat leak to the ambient. So there comes a temperature level, a ceiling actually, where this heat leak to the ambient matches the fixed heat current intercepted from the sun. So we'll call that temperature T max when Q dot 0 equals Q dot S. You see, in this particular case, this Q dot without a subscript would be 0, meaning there's nothing left to be given to the Carnot engine. So that means Q dot is equal to 0. And that also means that the efficiency equals 0. So hot collector is not good because it delivers nothing to the power plant. Or maybe a very, very cold collector would be good. How about that? That meaning I pendulate, I go in the other direction. The coldest collector is T equal to T0. Hey, wait a minute, we already know that the kind of collector is horrible because a collector as cold as the ambient does not represent a temperature level or so-called reservoir that differs from the ambient, and that means no engine. And this is how, by questioning the existing doctrine, you get the idea, more than the feeling, you get the idea that, wait a second, the way to go is somewhere at the intersection between these two asymptotes. Not too hot, not too cold, may be the way to go. So T should be greater than T0 and smaller than the maximum, which is actually known as the stagnation temperature of the collector, meaning you leave the collector out there in the sun and it will warm itself, if you don't touch it, it will warm itself up to this level. Dimensionless theta max is the name for the ratio T max divided by T0, and this ratio is equal to 1 plus Q dot S divided by UA T0. Clearly, W dot is Q dot S minus Q0. I make another move, which is to express the unknown temperature of the collector in dimensionless form called theta, T over T0. This move, which is called non-dimensionalizing, is based on recognizing a measurement that is independent of my choosing, and that measurement for temperature is the ambient temperature, T0. So I'm using T0 as a reference temperature scale. I used it first here for the stagnation temperature. Now I use it for this any temperature of the collector. Write the word any, because it is extremely important. It goes hand in hand with the word freedom. This theta could have any value, and it's up to me to tap into my imagination when it comes to these values. So these are all the let's call it nuts and bolts, or the meat and potatoes in the meal. If we use the formula shown so far, we're able to express this W dot. This is the object of the game, and the so-called object, which is the power to U, is non-dimensionalized with respect to something that's assumed fixed. This group here is U and T0 applied to the wind that blows by. A applies to the wind that carries the money out of your pocket and purchases this capital A. And on the right-hand side, we have two factors, each of which is depending on the temperature theta, collector temperature, and depending in kind of a contradictory way, because when this theta increases, the first factor decreases, while the second one increases. And that will take us quite nicely to the so-called key that opens the door. So we have a function called, I'll call this ratio W dot tilde, meaning dimensionless. A function of the only variable, which is theta, or T over T0. And this, as I wrote over here, the theta is free to vary between T0 and T max, which means that theta varies between 1 and theta max in dimensionless form. Furthermore, the function of interest is 0 for two values of theta, as I indicated earlier. W is 0 when the collector temperature reaches the stagnation temperature. And it is also 0 when the collector temperature reaches the ambient temperature. So this is 0 here, 0 here. And in other words, I'm making a drawing that's already in my mind. I don't have to make this drawing because it's so simple I can see it. But only I can see it. The only reason you see it is because I'm very generous to show you what only I know. And how big is W in these two special places? Easy, easy. When, well, obviously it's 0 when I said, but let's think about this other way. What is the value of each of these factors? I call them Roman 1 and Roman 2. Roman 1 is linear in theta, meaning it goes monotonically downward this way as theta increases. And the other factor is obviously 0 when theta equals 1, and it is 1 minus 1 over theta max here. And W is the product of these two factors, meaning the product of these two curves. And clearly, that product will be a curve with this particular shape. And now we have analytical representation of the hunch that the collector temperature of interest, the recommended one, is somewhere between the easy to identify extremes. Where exactly? Well, you can do it in two ways. I'm not going to teach you calculus because you know that. You can simply take, so two ways. Well, actually, lots of ways. I've already told you the first. The first is called hand waving, like somewhere in between, okay? Now, if you want to be precise, and this is in fact both the advantage and disadvantage that comes from learning and then believing in the calculus. The result from calculus, which means to take W tilde d theta and set it equal to 0, that takes you to an exact value for theta. That exact value is, it's called optimum. It turns out to be theta max to power 1/2. The square root of theta max is the precise best value for the temperature of the collector. In other words, the theta max would be this value on the abscissa, corresponding to this belly button of the bulging curve. I apologize for the metaphor here because belly buttons actually hang down, say, from the bottom of the belly of the cow. But in this case, I cannot talk about the belly button of the hump of the camel. I cannot say that. So, but you get the idea. It's a unique value for the temperature of this. The recommended temperature of the solar collector. The other way, meaning the third way to get to the answer, is to use the method of intersecting the asymptotes, which is to set these two factors equal to each other. In other words, to identify the theta that corresponds to that intersection. It is an approximate but much faster way to go about it. It also doesn't require knowledge of differential calculus. And from this move, which I teach in, sorry, I will not show you that here because I teach it in my course, Constructal Theory and Design, also Design in Nature, next semester. To get a feel for what we're talking about here, if the stagnation temperature, this theta max, say, example, say theta max equals 4, you can think what that means. If that means theta, sorry, T0 is 300 Kelvin, so the collector temperature, the stagnation temperature of the collector would be sitting out there, and the sun would be 3 times 4, that's 1200 Kelvin. And that means that the optimal theta would be 2. So that's a collector that has a temperature of 600 Kelvin. You know, from Kelvin to Celsius, you subtract 273 Kelvin and so on. And then the right-hand side that corresponds to this kind of design, that would be the maximum, meaning the one that corresponds to the peak. Every time you stumble upon something called optimum, you should take that with a grain of salt. The reason is that when it comes to performance, which is this level, there is a bandwidth of collector temperature designs that provide that sort of performance. So this so-called optimum is one of many, meaning it is embraced by a diversity of collector designs. The fact that the hump is flat-looking, like the surface of the horizon, looks flat, but it's actually curved slightly. That piece of physics is the physics or the reality of the birth of diversity. See, all these designs, from Spain to whatever, Amsterdam, or wherever they build these things, Japan, all these designs are performing the same way because they embrace the, I would say, elusive, highly precise optimum, to the point that what really matters is the concept, or the secret that a value for this collective temperature in between is valuable. Sorry to repeat the word, valuable. But any temperature in its vicinity is essentially as good as the mathematically precise temperature.